So I call this voltage difference. We're asking, what if you have more than one battery? And thankfully, it's kind of obvious. If we were to connect two 1.5 volt cells in series, what do you think the net voltage would be read on this voltmeter if we set them up like that? 3 volts. In other words, how many volts would go through this CD motor? Oh, sorry. Years ago, we used to listen to music on these wondrous little shiny discs called CDs. That was short for compact discs. And you would hear it whirring away, and they were sparkly in the sunshine. So, how many volts are going through this 10 ohm motor? 3 volts. By the way, if you wanted to read the voltage of the battery, you could do it in this circuit in one of two ways. You could touch a probe right here and right here. You could measure the gain in voltage, or you could touch a probe right here and right here. You could measure the loss in voltage. Because this circuit only has one resistor, either of those would give you the voltage of the battery. Because sometimes when you're trying to figure something out in a wiring system, you can't get behind the wall and measure where you want to measure, but you can often be clever and say, oh, that's going to be the same numbers if I measure over here. Okay. It says, explain your answer using principles of physics. I think it just makes sense. What did I say battery was like on a ski run? What was I calling it? It starts with letter C. Chair. I called it a chairlift. This would be like a 1.5 volt chairlift. Everybody gets off, and then they get on another 1.5 volt chairlift, and then they look down and, hey, we're 3 volts up the mountain. Okay. So in many portable appliances, CD players, flashlights, etc., 2 or 4 batteries are put together in series. That's a way to get more voltage, more energy per coulomb from a small battery. Okay? You may have noticed, so batteries, what did we say all of these standard batteries have as a voltage? Who remembers? I'll give you a hint, it's in the example. Yeah, these are 1.5 volts. That's a chemical reaction. Okay. You may see a squarish flashlight battery with like springs and twists on it. Those are 6 volt batteries. You can get the 9 volt. Those are the small rectangular ones. The 9 volt on your calculator. What's 9 divided by 1.5? If you actually, wearing face protection and eye protection and gloves, use scissors to cut apart a 9 volt battery, you'll literally find 6 small AAA batteries in series. That's how they get the 9 volts. Okay? Car battery is 12 volts. Car batteries, that's a different chemical reaction. That's a lead acid battery versus your standard carbon battery. But okay. What if we wired, the problem with doing this is each cell now has twice or 4 times as much current. The fact that the voltage went up and we got 3 volts, that also means if I go V over R, I have 3 amps of current. That means if one battery was being used, I'd only have 1.5 amps of current. 3 amps of current, I'm burning the batteries twice as fast. I'm draining the batteries twice as fast. But you might need, Evelyn, that many volts to run whatever task you're trying to run. Okay? Abby, Lean, you all with me? Okay. So wiring them in series, easy to get higher voltage, drains them twice as fast. If it's 2 batteries, drains them 3 times as fast if it's 3 batteries. That's why if you ever had a flashlight, one of those mag lights that has like 6 or 7 batteries, really bright, don't last very long. They drain the batteries crazy fast. What about wiring them in parallel? Okay, how many volts do you think are going through this resistor? Well, let's see. Let's ski this run. How many volts do we gain? How many volts must we lose? Yeah, here we're going to have a 1.5 volts running through that resistor, but in this system, these batteries will last twice as long. Why? Each of them is only having to contribute half the current required. And so a common workaround, if you look at my graphing calculator, which has 4 batteries, this thing needs 3 volts to run. But what they've done is they've put these 2 batteries in series, these 2 in series, but this imaginary 3 and this imaginary 3 are wired in parallel. So they managed to basically cancel out the using the batteries twice as fast by having an extra pair of batteries. That's why so often you'll see 4 batteries wired alternate, 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 alternate. 2 of them are in series, the other 2 are in series to get a bigger battery, and then we put the bigger batteries in virtual parallel, and that means we're not draining them twice as fast. Little nerd trivia for you there. Yep.
Do you think calculators are usually have the solar?
No. And batteries have gotten so much better. I'm seeing some calculators still have solar. They're not as effective. When we went to LEDs, where the solar cells, as I understand it, the ones on your calculators, they really needed UV light to work. These don't give off much UV. The old fluorescent ones that you grew up with, that you saw in kindergarten, that would flicker and then go on, what's actually inside, it's all UV. And they've painted the inside with a phosphorescent paint that will glow when exposed to UV light. That's why the tanning lights are all still those same ones. They're giving off just UV light. And that's what the solar cells typically were designed for. Now, they might be, with newer calculators, putting a different type of solar cell that works better with LEDs. But it's why if I dim the lights way down, I've had a couple of kids at the front, their calculator just stopped working. Wasn't enough to get it from, not enough energy from the LEDs. There's probably still some UV coming off there, but nowhere near as much. It's not like we're wearing sunscreen or anything like that, right? If I wanted to measure how many volts, if I put a voltmeter, this is the symbol for a voltmeter. It's 2 probes touching the wires at 2 different locations and a V for voltmeter. That would measure 1.5 volts. If I put an ammeter in the circuit, I would find each of these is contributing half of the total current. So they'll last longer. What if we have batteries facing each other? That's how we recharge. If we have voltage sources facing each other, rechargeable batteries are charged by connecting them to a cell that forces current back through the cell. So if we connect a 1.5 volt cell to a 6 volt charger, first of all, what would be the direction of the current? The current will be going this way because that's the higher hill, 6 volts. If we wanted to give that a direction, counterclockwise, or you can write counterclockwise, but the abbreviation for counterclockwise is CCW. The abbreviation for clockwise is CW, and you've all had me enough to know that I tend to abbreviate if I can. What would this voltmeter read? I'll give you a hint. It wouldn't read 6 and it wouldn't read 1.5. If you gain 6, and then this is going backwards, so I guess you lose 1.5, what's the net voltage? Yeah. How many volts are going through this protective resistor? Why do we have to have a protective resistor? So that extra little 1.5, that's what's going into recharging the battery, but we still have 4.5 volts. We don't want to heat up the wires. We've got to bleed that energy off. That's why if you've ever plugged in a little battery charger, they all have a little light up display thing. That's just bleeding off the extra voltage to make sure that the wires don't get hot. So, in my ski hill analogy, 2 cells in series, let's suppose we have a 6 volt and a 6 volt. That's like a 2 chairlift ride up the mountain. You gain 6 volts, you gain 6 volts. Mathematically, that's identical to having a single 12-volt chairlift. And here's where my analogy breaks down. Somehow these 2 6-volt chairlifts have twice as many benches because your current would double. You can get more skiers up. Okay? You would be losing 12 volts through here. Cells in parallel are like two chairlifts that both lead to the same spot. So half of you go on that chairlift, half of us go on this chairlift. We all end up at the same location at the top of the mountain. And because we're all ending up in the same location at the top of the mountain, each chairlift only has to carry half the people, half the current. Opposite cells are like one up chairlift followed by one down chairlift. In my analogy, everybody rode a 6-volt chairlift, but then some people, to get to a certain hill, had to ride down a small chairlift to get to a really neat ski hill. They gained 6, they lost 1.5, now they're 4.5 volts high. So by properly labeling the circuit, we can see the difference in voltages. I think in the homework, there's a couple of multi-battery questions. I'm not going to give you a multi-battery question on the test. I'm just doing this because it's kind of neat. And also because, principles keep in mind, positive means higher, negative means lower. Current goes downhill from the highest voltage, positive, to the lowest voltage. Positive to negative means a loss. If you're having to go backwards through a resistor just to follow a ski run, that would be a gain. That would be as though the skiers decided to all ski up the hill just by pushing themselves up the hill. So that brings us to a pretty challenging question. Example 6 says, find the voltage difference between points X and Y, and then find the unknown currents and voltages using Kirchhoff's laws. I am not going to give you one this tough. In fact, it says the complete analysis of this is beyond the level of Physics 12, but we should be able to do voltage and currents. Okay. Who remembers what was the first thing I always tried to do? What was step 1? I'm going to label downhill. Where's the highest hill, the highest chairlift in this question? 6 volts. Downhill, I know definitely is here, which means I can circle that. I know it's going that way. It's going that way. What direction must we be flowing in the top right here? Yeah, because I've got current coming in and current coming in. It's got to go out somewhere. So we're going this way. We're going this way. Well, I guess we're going this way and like that. Okay. Step 2, we'd like to try and find the total current. I said, look for amps. Do I have amps anywhere? Where? The 0.5? Okay. Does that mean there's 0.5 amps right here? No, because more flowed in. But let's backtrack. Oh, how many amps going through here? Knock, knock. I know 2 things. I know all 4 things, but they didn't ask for power. I'm going to get voltage. V equals I times R. I think this is also 1.5 volts, is it not? Okay. Yeah. Is there anywhere else I know 2 things? No. Then I'm going to try and ski. Now there's 3 ski runs. Starting with the 6 volt, that's a ski run. I'm a little, because we're going backwards through the chairlift battery right over here. I might save that for last, maybe if I can. Maybe I'll have to, though. I don't know. There's this run. The problem with this run, I don't know that voltage. I don't know that voltage. I don't think that's going to help me. Where else? Well, that's a ski run. And as I look at this one, you know what, Callie? I know the voltage here, 1.5. I think I can figure out how many volts must be here. I don't know R yet, but I can figure out how many volts. So let's ski that run, Callie, you and I. So, how many volts am I starting out with this battery? Did it go this way? I don't know how many. How many volts did I lose going through this resistor? What do these 2 resistors' voltages need to add to? How many volts must I lose going through here? Good. Why does that help me? Anybody see it? What ski run can I do now? The outest one. Yes, the outest one. The outer one. So here, I start with 6. I don't know. How many volts do I lose going through here? That got me to the bottom. How many volts must I lose going through here? Has to be 6 take away 2.5, which is 3.5. Knock, knock. I know 2 things. I know the current there. How can I figure out the current there? It's going to be V over R. You're not going to reach for your calculator because it's going to be 3.5 divided by 3 point what? 1 amp. Oh, how many amps right here in the question mark? Okay. Ooh, how many amps in this question mark? Not 1. 1 coming in, 0.5 coming in. Ooh, how many amps going through mystery resistor R? I know 2 things. What is mystery resistor R? It's going to be V equals I times R. R equals V over I. It's going to be 2.5 divided by 1.5. I have no idea what that is. It's not 16. There's no way it's 6. 1.67? Okay. So let's see. Now I'm just going to make sure I found everything. I found all 3 things there. I found all 3 things there. I found all 3 things. I'm good. Oh, the final thing it wanted was the voltage difference between X and Y. Right? I think that's what it said. Okay. Well, what do I lose going through this ski hill? What do I gain going through the chairlift? Lose 1.5, gain 4. And I also could have figured it out because technically this section here and this section here are in parallel. It's going to be 2.5 volts a piece. Yeah. So I'll answer the question that they wanted me to find. Okay, let's do that. I solved everything, and then the voltage between X and Y was 2.5 volts. And we were able to figure that out without rewriting this circuit. Let me emphasize, I'm not going to give you one that tough. That's kind of nice. We can handle it. Yeah.
Don't have 1.5x of the x place, not 0. So it actually
It works no matter which way you do it. Okay. Hey, go 6 gain minus 4 because we're going backwards through the chairlift. Oh, sorry. 6 gain minus 3.5, 2.5, minus 4, that's negative 1.5, but now we're going backwards up a hill. We'll gain 1.5, gets us to 0. No matter which way I ski it, as long as I'm meticulous and pay attention to my directions, I'm good. Pardon me?
Yeah.
Okay. What's your homework? Try number 2. Try number 3. Number 3, they didn't tell you what direction the current is flowing, just so that all of you get the same picture. Let's have the current flowing from X to Y, but you get the same answer if it was going from Y to X. Okay?
Sorry, so you've assigned every question?
No, I have not. I assigned 2 and 3. I skipped 1.
I didn't do that.
I know. Okay, attention span. Number 3, you don't need to rewrite it, because they told you 2 amps goes through this 3 ohm resistor. That's your crack in the armor right there, and everything else follows. It's actually a really neat one. I'm not going to give you one as tough as number 3 on your test. It's a nice little brain teaser, though. 4 is good. A and B. 5 is good. 6 is good. 7. Do you have to rewrite number 7? You might. Yeah. I don't see 2 things anywhere. I can't remember. You might have to rewrite number 7. 8 is good. 9 is good. 10 is good. 11 is good. But you got lots of time to work on the take-home quiz and work on this. Let me stop the video. So if you want to get out the ultimate review, okay, give me a second. Someone said they don't have it. Can you all get out the ultimate review, please? That you can cross out because I skipped these topics. So, Lean, you ready? Here we go. That's fine. That's fine. That's fine. We're just quickly going through the ultimate review. I'm telling them which questions you can skip. Gravity, that's good. That'll work. I definitely like number 12. 14 is good. 17 is good. You can cross out 23 part. You know what? You can cross out 23 because I didn't do electric potential with you.
21 is good.
I don't know. I'm just going along here. So you can cross out 23. That looks good. Electric field. That'll work.
Oh.
Polarity is good. 37 is good. 41 is good. Yeah, it's 2 reviews in one. That's what I said. 47 is good. There's the answers. Okay, this is what we need to look at. The circuitry review, part 2. You can cross out number 1. I didn't cover how you put in ammeters and voltmeters. I skipped that. There's another one of those showing up, I know. That's good. That's good. You can cross out number 13. You can cross out number 18. Number 21 is asking you the potential difference. That's voltage. You'll figure it out because there's a variable V next to the battery. So that's a great question. I've been using the term voltage instead of potential difference. 22 is good. 23 is good. 24 is good. 28 is good. You can cross out 29. Cross out 30. 33 you can cross out. 37 you can cross out. More ammeter, voltmeter placement. That's good. That's good. That's good. Yeah, scholarship questions. Honestly, 55 isn't that tough. You could try it. It's about as tough as the one we just did at the end of this lesson. Oops, I don't want to do that, Mr. Dueck. Let me go pause the recording.